Hey guys, so this is the chapter 5 video for 1211. I'm picking up on slide 15 of the PowerPoint. In the previous video I did the heating curve. Now we're going to work a problem that takes us through all the steps involved in the heating curve. At most, if you are doing a heating curve of a normal substance that goes through all three phases, when you do a problem you would have to do 5 steps. If you are doing a problem that only takes you through some of these steps, you may only have to do 2 or 3 or 4 steps, okay? So whenever you read a problem, you have to decide on where your starting point is and where your finishing point is, and you do the steps that are required for that problem, all right? Sometimes students get carried away. They think that for every problem you should go through all 5 steps. That is not correct, okay? You have to be smart about how you approach the problem and do it the right way. So the problem in the slide asks how much heat must be absorbed to take 25 grams of ice from -10 degrees until it becomes steam at 100 degrees Celsius. So I'm going to label on my graph, starting at -20 on my graph, but this problem specifies I'm going to start at -10. So I'm going to use my green marker and say I'm going to start at that spot right there, and I'm going to go until I have steam at 100 degrees. So 100 degrees, this whole horizontal line is at 100 degrees. But if I'm on the left side of the line, that's the end of the water side. So this is liquid water. In the middle of it, I'm going to have a mixture of water and steam. And finally, when I get over here, that's going to be steam at 100 degrees. So that's the point where I'm going to stop my problem. So essentially, to work this problem, I'm going to have to do a little bit of the first segment, which I call from the left to right. I named these 5 steps Q1, Q2, Q3, Q4, and Q5. Okay, so I'm not sure if every textbook is going to label it the same way, but the first segment is Q1. I am going to do part of that step, so I'm going to have to do a calculation for Q1. Q2 is the horizontal for melting. I'm going to have to do that step too. Q3 is warming it up to 100. I will do that step. And then Q4 is the boiling. I'll do that step, it's Q4. But then I do not need to do any Q5 because my problem stops right here, so I don't need to go past that point. So I'm only have to do 4 steps here. So I'm going to get rid of Q5. Okay, now I'm going to have to do a calculation for all 4 of these steps, but if I want to heat the ice from the beginning to the end, if I want to do the whole process, that means that when I get the answers for these 4 steps, I'm going to add them together to get the total. I want to know the total amount of heat it takes to warm up the sample through all the steps. Okay, so the problem said it was 25 grams of ice starting at -10. So Q1 is going to be MC delta T. The mass is 25 grams. The specific heat of ice is not the same as water. You have to look that up. If you look in the appendix B, the specific heat of ice is 2.092. So I'm going to plug that in right here. Joules per gram per degree Celsius. Then I have my delta T. In Q1, my delta T, I'm heating it from -10 to 0. Only that part is happening in that leg. Okay, again, students get carried away with the delta T. They want to do all of it at once, but I can only do the part that corresponds to this segment. Okay, so from -10 to 0, that's a change in temperature of 10 degrees. So delta T is going to be a 10. Okay, that takes care of Q1. Calculate that. That'll be the joules used for required for Q1 to be absorbed. Now I do Q2. It's melting. For a phase change, I'm always going to do M times delta H. The units have to match. So the delta H that is in our appendix is kilojoules per mole, which means I need to know the moles of the water. So I'm going to multiply the moles of water, which to get the moles is 25 grams of water. To get from grams to moles, I divide by the molecular weight. So I'm going to go ahead and write up here 25 divided by 18. That is the moles. I think it's 1.3 or 1.4 something, whatever. But if you do 25 or 18, that's going to give you the moles of the water that we have in this problem. Okay, then delta H, it's the heat of fusion, is 6.008 kilojoules per mole. Okay, so that's Q2. In order to melt that much ice, it's going to be the moles of the ice times the heat of fusion. The moles cancel. It's going to give you the answer in kilojoules. Now, if you're paying attention to units, you'll notice the answer for Q1 is in joules. The answer for Q2 is in kilojoules. Before we can add them together, we're going to have to decide which one we want. Chances are, if we add all these numbers together, if the answer was in joules, it'll be a really big number. And normally when it's a really big number, that's when we want to shift it into a bigger unit so the number is more manageable. So typically on these problems, when you're doing all these steps, your final answer probably needs to be in kilojoules. If I don't specify, I don't care which one you do, but often the problem will tell you to put the answer in kilojoules just because that's an easier number to deal with. Okay, so Q3. Now I warmed my ice up to 0, then I melted it in Q2. So now Q3, I'm going to warm it from 0. I don't have to go all the way up in every problem, but in this problem we do. I want to get all the way over to this point, so I have to go entirely through that whole segment. So my mass, again, is going to be 25 grams. My specific heat, this time it is liquid water, is 4.184 joules per gram per degree Celsius. And then my delta T, I'm going from 0 to 100. That delta T is 100 degrees Celsius. I'm doing the entire segment of Q3. Finally, my last step is another phase change. Phase changes are always the M times the delta H. So again, my moles will be the 25 over 18. That'll be moles. And then my delta H, this is the heat of fusion, is 40.67 kilojoules per mole. Once we get all these answers, we need to put them all in kilojoules and add them together, and then my answer will be some number of kilojoules. Okay, and that is it. I will go back in a few minutes and put in the answer into the PowerPoint so you can double check. But that is the setup. If you get the answers, put them all in kilojoules, add them together, should come out pretty easily. So hopefully you got it. Okay, so now I'm going to go back to the PowerPoint. So now we've done some calculations, just introducing the idea of how heat is involved in a process where if we heat things up and cool things down, the temperatures change, you can change physical states. But what we haven't done yet is talked about how that applies to chemical reactions. Okay, if we do a chemical reaction, like say I take gasoline and I burn it, we know that when we burn gasoline, it gives off heat. That is a exothermic process, but we need to go through like, okay, if I burn a certain amount of gasoline, how much heat's going to come out? We need to correspond the heat to the balanced equation. All right, so we need to define some terms. First of all, the word enthalpy is just a fancy chemistry word that stands for the heat content of a sample. So we use the letter H to stand for the enthalpy. But then most of the time we don't refer to enthalpy as a single thing. We refer to, if we do a chemical reaction, the reactants have a certain amount of heat stored in the molecules, the products have a certain amount of heat stored in the molecules, and the difference between those two heat values is called delta H. Okay? It's the change in the enthalpy during a chemical reaction. So we get it. The delta H is the final heat content minus the initial heat content, which means the product values minus the reactant values to get the delta H for a chemical reaction. So if we have an exothermic reaction, we need to think about, okay, if it's exothermic, that means it's giving heat away. So is the heat content of the sample or the system increasing or decreasing? Okay, well, if we're giving heat away, that means we're starting with more heat, we give some away, that means we end up with less heat. So an exothermic reaction, the final amount of heat is less than the initial amount. And if I do a small number minus a big number, that's going to give me a negative delta H value. So delta H for an exothermic reaction is negative. Delta H for an endothermic reaction is going to be positive. That's an important thing to remember. It's going to come up a few times in the next few slides. So delta H is also based on the stoichiometry of the reaction. Now the word stoichiometry started coming up last chapter, or actually in chapter 3, where any calculations that you do using a balanced chemical equation and using the ratios of the products and reactants and all that kind of stuff, that is called stoichiometry. So when I do a chemical reaction, if I react 5 moles of reactant, then it's going to give me a certain number of moles of product based on a ratio. The same principle applies to the heat amount. If I burn a mole of gasoline, there's a certain amount of heat that's going to come out of the reaction. If I burn 2 moles of gasoline, it's going to give off twice as much heat. So again, there's a ratio between the amount of reactants that you react and the amount of heat that's either absorbed or released, depending on the reaction. Okay, so that's what the word stoichiometry means. It just refers to those relationships that we've been setting up through chapter 3 and 4. So we need to be able to draw what's called a energy profile diagram. It's a pretty simple thing. Now I will say this graph that I have on the whiteboard right now is called a heating curve. The graph we're about to draw is called a reaction profile or an energy profile of a reaction. They're 2 different graphs. If you're asked to draw one of them on the test, make sure you draw the right one. Okay, a lot of students get confused. And if I ask for the energy profile of a reaction, they draw this. If I ask for the heating curve, they'll draw the energy profile. So be careful about that. But essentially, this graph is pretty straightforward, where, again, you always have to have your axes. You're going to have some form of energy on the y-axis. Sometimes it's called free energy, sometimes it's called internal energy. There's different ways of labeling it, but it's energy on the y-axis and it's progress of reaction on the x-axis. Sometimes they'll just label it reactants yielding products. But basically what we're saying is, on the left side, we're going to start with our energy of our reactant molecules. As we move to the right, that means we're turning them into the products. Okay, just like a reaction on the left side of the reactants and on the right side of the products, that's how we're organizing this graph. So when we do this, we're going to arbitrarily just say our reactants have some amount of energy. So we're just going to put a level there, put R for my reactants. Then, if I turn them into products, and so I'm looking at slide 17 right now. On slide 17, it says delta H for a reaction is negative 483.6 kilojoules. So what that means is if it's negative delta H, that's an exothermic reaction. It means that my reactant molecules have a lot of energy in them. And during the reaction, they release energy to the surroundings. So I end up with the product molecules have less energy in them than the reactants did. So my product energy is going to be lower than my reactants. Specifically, the difference in the y-axis is going to be 483.6 kilojoules. Okay, so that's the amount that the energy levels differ from each other. Now, in between, and this is something we'll learn more in 1212 about this topic, but for now, when molecules collide with each other, which anytime you have a reaction, the molecules have to collide with each other, there's always going to be an energy barrier that has to be overcome for the reaction to occur. Okay? If molecules just kind of bump into each other, when they do that, they bump, and most of the time they just bounce off and fly away or do whatever they want to do. But every once in a while, if they crash into each other hard enough, if the molecules crash and I can break a bond, once I break a bond, at that point, then I have the potential to make a new bond, because breaking a bond creates unstable fragments of molecules that all the atoms want to have a certain number of bonds, and if they lose one, then they need to make another one to replace it. So there's this energy barrier that has to be overcome, which involves breaking a bond. It's going to cause a big hump in the middle of the graph in between the reactants and products. Okay, so I'm going to draw a hump there. That hump from the reactant energy level up to the top, that's going to be called the activation energy. And it's an energy barrier that has to be overcome for the reactants to turn into products. Basically, sometimes my reactants might be really stable molecules, and if they're really stable, why would they want to change? So what happens is something comes in and crashes into a molecule and breaks it into pieces, and once it breaks into pieces, those pieces are unstable. In chemistry, when something's unstable, we usually mean it has high energy. Things that are high energy aren't stable. They want to form bonds to make them more stable, which takes them to a lower energy state. And once they get to a lower energy state, that's usually where they want to stay. Okay? So this is what an exothermic reaction energy profile looks like. The reactants are high, the products are low. There's a barrier in between. We'll talk more in 12.12 about how big that barrier is, because that affects how fast the reaction is, which is called kinetics. Okay. Now, if I looked at a endothermic reaction energy profile, it would look a lot like this, other than the fact that my reactant energy level would end up being less than my products. So I would end up switching these. On an endothermic reaction, the product energy would be higher than the reactant energy. Okay? But otherwise, the setup and how I label things would be exactly the same.